This video introduces Riemann sums and mentions their relationship in the definition, the relationship to the definition of the definite integral. So Riemann sums are named after German mathematician Bernhard Riemann. And Riemann shows up all over the place in mathematics, like Riemannian geometry, on which Einstein's theory of relativity is based, and there's like the Riemann hypothesis, and there's a lot of sort of famous math stuff associated with him. So we're going to talk about something that he did to approximate area under the curve. So we've learned already about like left endpoint approximation, right endpoint approximation. So what Riemann sums does is approximate the area under the curve a little bit more generally, so the rules aren't quite as strict. So let's just look at this. So say I want to calculate the area under this curve from A to B. So remember, we're thinking about sort of taking this, and we want to think about all of the area under the curve here, all of this. How much is that equal to? And we talked before about like one method is to sort of divide this into equal subintervals, and then you choose either the left points to represent rectangles or the right endpoints to represent rectangles. And we're going to do something similar to that here, except now we're going to allow our subintervals to be various lengths. So maybe these are our subintervals. Right, this one, and then we've got a littler one, then a medium one, right? So before we insisted that they were the same length, each subinterval, now we're allowing them to be anything. And then also, when we're choosing the points that can represent height for the rectangle, we're no longer going to insist that we do that the same in each subinterval. So for example, maybe in this subinterval, I'll take my height at the left endpoint. So that gives me this rectangle. And this one, maybe I'll take the center. So that gives me this rectangle. This one, maybe I'll take one that's just kind of on the side, nowhere sort of in particular, just a random point in the interval. Maybe this one I'll take the right endpoint. So give me this one. And then maybe again somewhere approximately in the middle and giving me this rectangle. So again, the idea is we're approximating the area under the curve. So this area, if I add up this and this and this and this and this, that's going to give me a sort of rough approximation of the area under the curve. And the idea is that if you sort of choose well, right, like if I had chosen better subintervals and better sort of representative points from each of these, then I would get a pretty good approximation of the area under the curve. So this is a lot more flexible than, say, left endpoint or right endpoint approximations. So we've got these subintervals, and they don't have to have equal width. So subintervals can vary in width. And our sample points, so those are the ones that I indicated with X here, so like left endpoint, midpoint, somewhere here, right endpoint, middle, those can vary in location with each subinterval, right? So that you don't have to take all left endpoints or all right endpoints or whatever. You can just sort of take them wherever you want. So these are the sort of hallmarks of a Riemann sum. So let's just calculate one of these. Let's just do a problem. Approximate the area under the curve of this function f of x equals x squared minus x over the interval from 0 to 4 using these partition points and these sample points. Okay, so first of all, usually if you're doing a Riemann sum problem, you are given the partition points and the sample points. So the partition points are telling you how to break up your subintervals. So this is telling me I'm going from 0 to 4. 0 to 2, that's my first subinterval. 2 to 3, that's my next one. 3 to 7 halves, and then 7 halves to 4. And what we're doing is just sort of like choosing the places to break our intervals, right? And this isn't really a true partition because I'm allowing 2 to sort of be in both of these, and I'm allowing 3 to be in both of these. But that's not too big a deal. And then the sample points, you should have one from each subinterval. For example, 1/3 comes from the subinterval 0 to 2. 5 halves comes from the subinterval 2 to 3. 3 comes from the subinterval 3 to 7 halves, and 4 comes from this subinterval. So this is sort of what I'm doing like in this picture, right? I'm chopping this up into unequally sized subintervals, and then I'm just taking a point in each of these things. It can be the left point, it can be the right point, it can really be anything. So this will be, so the Riemann sum in this case will be equal to, if I want the area of that first rectangle, I need to take the width of the rectangle, which in this case is 2, right? The length of this subinterval. And then I'm going to multiply it by the height, which is going to be where my sample point hits the curve, right? So this is going to be the width, this is going to be the height. And then similarly, here width 1, height f of 5/2. Here width 1/2, height f of 3. Here width 1/2, height f of 4. So this expression, my Riemann sum, is really adding the area of each of these 4 rectangles, right? So like I'm taking these rectangles, I mean this is obviously a different picture, but I'm taking these rectangles and I'm going to add up all their individual areas, and that's going to give me the rough approximation for the area under the curve. So each of these represents sort of width times height for each of those rectangles. So in this case, f of 1/3, my function was x squared minus x. So let's give me some white space here. So 1/3 squared is 1/9, so minus 1/3. And then that 1 times 25/4 minus 5/2. 1/2, 9 minus 3, and 1/2, 16 minus 4. So then I end up with making common denominators here, right? -2/9, and I multiply that by 2, so -4/9. This one becomes 25/4 minus 10/4, so 15/4, because I'm multiplying by 1. This one is 6 times 1/2, which is 3. This one is 12 times 1/2, which is 6. So then I need common denominator for these two things, right? So then this is -16/36. This is 135/36, 9 times 15. And then plus 9. So then this is 119/36 plus 9. And then if you make a common denominator here, you ought to end up with, oh, let me just punch this in. 9 times 36 is 324. So 119 plus 324 all over 36. So 443 over 36 square units. So this is the Riemann sum given these particular partition points and these particular sample points. The main idea with Riemann sum is that you get more flexibility doing it this way, right? You're not sort of fixed in terms of how you choose your subintervals. You're not fixed in terms of how you choose your sample points. So in some sense, it's a better approximating tool for sort of finding the area under the curve. So this is what a Riemann sum is, and so that leads us to the definition of the definite integral. So the definite integral of f over a closed interval a to b is the limit of Riemann sums and is denoted by the following. So we've got this elongated s, which is the integral symbol, which we know is associated with antiderivatives, right? But in this case, we're not using it in the antiderivative way, although we'll come to find out shortly that those are related to each other. This lower limit of a tells me where to start my interval. The upper limit of b tells me where to stop, and I'm sort of taking the area under this curve, right? This is the definite integral. And this essentially says we're taking the limit of the Riemann sums where we essentially have infinitely many subintervals that are all infinitely thin, right? And I'm sort of taking the limit where this sort of delta xi is the width of the ith subinterval, and it's going to 0. So like essentially all my subintervals are infinitely thin, and I've got these infinitely many rectangles, and I'm adding up the area of these infinitely many rectangles, and that's supposed to give me like the sort of the definite integral. So we'll talk more about this. Don't get too bogged down in this notation, but this is sort of a formal way of writing the idea of having infinitely many of these rectangles and letting their widths go to 0. So that's the definition of the definite integral. Luckily, you don't necessarily need Riemann sums to calculate these. We usually use something else, which we'll talk about in another video. But before we end this one, let me just make a comment that you may remember for left endpoint approximation and right endpoint approximation, we insisted that the function was continuous and positive. But we didn't do that for Riemann sums. So in particular, if you go up here and look, when we did this height interval for, say, f of 1/3, we ended up with a negative number, right? So like the first rectangle has area -4/9. Like, what is that supposed to mean? So it turns out that what we're calculating here is not really the area under the curve, but the signed area under the curve. So if you have a height representative that's negative, right, then that's essentially going to give you a rectangle that lives below the axis. And when you calculate the area using the formula that we just suggested, right, you're going to end up with negative area. So the signed area under the curve is anything that's between the curve and the axis and above the axis counts as positive area. Anything that's between the curve and the axis and below the axis counts as negative area. So if you take the signed area under the curve, what you're doing is sort of adding up all the positive areas and you're subtracting all the area that's beneath the curve. Okay, so in some sense it's like net area, like how much area is either above or below the axis. So that's also sort of good. Another sort of point in favor of Riemann sums is that we need fewer restrictions on our functions. Like if we could only think about functions that are always positive, that's not that great, but Riemann sums allow us the ability to sort of think about the signed area where we think about stuff that's under the axis as well as stuff that's above the axis. Okay, so this is an introduction to Riemann sums and how they are used in relationship with the definition of the definite integral.